Welcome! In this video, we'll explore how OFDM systems use MIMO to boost wireless performance. We'll break down the core ideas, what it is, and why it matters. Then, we'll jump into a MATLAB simulation to see it all in action. Let's get started. MIMO, or multiple input, multiple output, is a key wireless technology that uses multiple antennas at both the transmitter and receiver ends to significantly improve performance. With this technology, we can transmit multiple data streams at the same time, over the same frequency, and in the same time slot. In an OFDM system, this is done by generating a separate OFDM grid for each transmit antenna. Each grid carries its own data stream. Then, we perform OFDM modulation on each grid, just as we covered in earlier videos. Now, let's walk through a simple 2x2 MIMO example. Each of the two transmit antennas sends its own independent data stream. For instance, using a 16QAM constellation. These streams travel through the wireless channel and are captured by two receive antennas. Because each transmitted signal can reach each receiver through different paths with reflections, delays, and interference along the way, we effectively have four distinct wireless channels. Each receiver picks up a mixture of both transmitted signals, each one altered by its own channel conditions. So what we get at the receiver is a superposition of the two streams. This causes the received signal constellations to look messy or distorted. They're no longer clean points like in the original 16QAM, which means we can't demodulate them yet. To decode the original streams, we'll need to undo the effects of the channel. Let's take a closer look at the math behind this. We're dealing with a system of two linear equations with two unknowns, the transmitted symbols. Using linear algebra, we can express the system in matrix form. In this form, the received signals are represented as the product of the channel matrix and the transmitted signal vector. To solve for x1 and x2, we simply multiply the inverse of the channel matrix by the received signal vector. This gives us an estimate of the original transmitted symbols, effectively separating the mixed signals at the receiver. To fully understand MIMO systems, there's one crucial question left. How do we estimate the channel responses? If you've seen our video on channel estimation, you'll recall that in OFDM systems, we use special known pilot signals embedded in the transmission to estimate the channel. With MIMO, we add a separate set of pilot signals for each transmit antenna's OFDM grid, carefully arranged so their pilot positions don't overlap. We also make sure that at each pilot location, no other data is transmitted on the other grids. This way, when the receiver captures the combined signals, the pilots from each antenna can be isolated. As a result, at each receiver, the pilots reveal the channel effects of the corresponding transmit antenna alone. Using this method, we can accurately calculate separate channel estimates for each transmitter-receiver pair, following the same principles explained in our earlier video. Now, to see how this works in practice, let's walk through a MATLAB simulation. You'll find the full code linked in the video description. We begin by setting up the simulation parameters. First, we define the number of subcarriers and symbols, which determine the size of the OFDM grid. Then, we set the subcarrier spacing to 15 kHz. Next, we choose the QAM modulation order for both the user data and the reference signals, along with the length of the cyclic prefix. We also define the pilot density in both frequency and time. This controls how often pilot symbols appear in the grid. Finally, we prepare the user data. In this example, we'll transmit two short text messages, one on each transmit antenna port. Next, we compute where to place the pilot signals in the OFDM grid. We start with the first antenna port, placing pilots based on the defined densities. Then, for the second antenna port, we generate a separate set of pilot positions, making sure they don't overlap with the first. We also calculate the data positions, the remaining locations in the grid not used by pilots. To visualize this, we generate a plot showing the pilot and data positions. As you can see, pilots are inserted every fourth OFDM symbol and every fourth subcarrier, and each antenna port uses a distinct, non-overlapping set of pilot locations. Next, we move on to generating the QAM symbols. We start by creating variables to hold the data bits, data QAM symbols, and pilot QAM states. For each of the two transmit antenna ports, we take the predefined user data, convert it into a bit stream, and repeat it as needed to fill the data portion of the OFDM grid. To do this, we use helper functions available via the link in the video description. Then, we modulate the bit streams using a QAM modulator function. We specify the modulation order, use gray coding, set the input type to bit, and normalize the average power to 1 watt. For the pilot symbols, we generate random integers between 0 and 3, then modulate them as well using the same function. Now we're ready for OFDM modulation. We first initialize placeholders for the two OFDM grids and the corresponding time domain signals. Then, for each transmit antenna port, we build its OFDM grid by inserting the modulated data and pilot symbols into their designated positions. After that, we apply the OFDM modulator function, passing in the grid, number of subcarriers, and cyclic prefix length, converting our signal from the frequency domain into the time domain. Finally, we plot the transmitted constellations, using different colors for each antenna port. As you can see, both use 16 QAM. You may notice that one of the constellations has some points missing. That's because the text message for that port is short and doesn't cover all possible bit combinations. Next, let's model the effect of the wireless channel. We start by calculating the sampling frequency, which is simply the number of subcarriers multiplied by the subcarrier spacing. To simulate the channel, we use MATLAB's built-in MIMO channel function. We begin by passing the sampling frequency as the first parameter. Then, we define the path delays in seconds and the corresponding path losses in decibels. To simulate a slowly changing channel, we set the maximum Doppler shift to 5 Hz. We'll assume no spatial correlation for simplicity. We also specify the MIMO configuration by setting the number of transmit and receive antennas to 2 each for a 2x2 system. Finally, we configure the random stream and seed to ensure repeatable results. This channel model returns 2 received waveforms, one for each receiver, just as we described earlier in the theory section. Now, let's move on to OFDM demodulation. For each receive antenna, we use the OFDM demodulator function, passing in the received signal, number of subcarriers, and cyclic prefix length. To visualize the result, we plot the received OFDM grids. As you can see, the QAM symbols are clearly distorted due to channel effects, making it impossible to decode the data correctly without further processing. Now, let's estimate the 4 individual channel responses, as we discussed earlier. We start by generating the pilot locations and the full grid of target locations for interpolation using MATLAB's mesh grid function. If you're unfamiliar with how this interpolation works, feel free to check out our dedicated video on the topic. Next, we loop through each combination of transmit and receive antenna ports. For each pair, we estimate the channel response by dividing the received pilot values by the known transmitted ones, following the method shown in our channel estimation video. We then interpolate these sparse channel estimates across the entire OFDM grid using the interpolate 2D function, passing in the pilot positions, estimated values, and the full grid coordinates. With channel estimates now available at every point in the grid, we're ready to perform data equalization. We loop through each subcarrier and OFDM symbol. At each resource element, we construct a 2x2 channel matrix using the interpolated values. Then, using linear algebra, we estimate the transmitted QAM symbols by multiplying the inverse of this channel matrix with the received values. Finally, we visualize the equalized constellations. As you can see, the 16 QAM structure is now clearly restored, and we can correctly identify the transmitted symbols. In the final step, we demodulate the received QAM symbols to recover the original user data. For each transmit port, we extract the equalized QAM symbols and apply the QAM demodulator function. We specify the modulation order, use gray symbol mapping, and set the output format to bit. Next, we convert the demodulated bit streams back into text using a predefined decoding function. Finally, we compare the received bits to the original ones to calculate the number of bit errors and the bit error rate. These results are displayed in the console. As you can see, the transmitted messages are mostly recovered. However, due to channel impairments, a few bit errors remain, which result in minor distortions in the decoded text. And that's all for today. If you have any questions, feel free to leave them in the comments down below. See you in the next one.